Hi everyone. In this section we will explain molecular orbital theory. Now we would need it also for the next chapter, which is the benzene, since we are talking about conjugated systems. We will focus on molecular orbitals for just the conjugated system, but we will explain a little bit how sigma molecular orbitals are formed, and then we will carry on to the pi molecular orbitals in there. So what is a molecular orbital? Molecular orbitals, these are formed by combination of atomic orbitals. And molecular orbitals gives us the whole picture of figuring out how electrons are distributed not in an atom, in a molecule. Now we've studied how electrons are distributed in an atom by looking at the atomic orbitals. And let me remind you, the atomic orbitals are the s orbitals and the p orbitals in there, and the d and the f. These are the atomic orbitals. So when you draw the electronic configuration, the 1s2, 2s2, 2p6, and so forth. These are the electronic configuration of the atom, okay? Not the molecule, the atom itself. Now, if atomic orbitals combine, then you will form molecular orbitals. So let's say, for example, if you have the s orbitals combine. So if the s orbitals combine in there, you will have the sigma bond. The s orbitals are circular in shape. So if you have two s orbitals in there, and these two s orbitals, each one of them has one electron. If these s orbitals, they combine, this means that they overlap with each other, then you are going to make a sigma bond. You're going to make a sigma bond in this case, where every bond has two electrons. And that sigma bond is called the sigma molecular orbital. Now, on the other hand, if you have two p orbitals in there, each p orbital has one electron, and if the p orbitals, they combine with each other, then you are going to have an overlap of these two p orbitals, and the p orbitals will make a pi molecular orbital, pi bond molecular orbital. This is going to be a sigma bond molecular orbital. So the molecular orbitals, they do explain how the pi and the sigma bonds are formed. So they do explain how electrons are distributed in a molecule and not in an atom. And molecular orbitals, they are the combination of atomic orbitals. So let's have an example of hydrogen molecule. If you want to draw the molecular orbitals of hydrogen, I know that hydrogens have a covalent bond, right? The bond is a sigma bond. So let's go ahead and draw that in the molecular orbital there. Hydrogen has it's one atomic orbital, so its electronic configuration is 1s1. So every hydrogen has one electron in there in the s orbital. So you draw these two hydrogens in there because, again, you're forming a bond between two hydrogen atoms. So you draw each hydrogen has a 1s atomic orbital, and in this 1s it has one electron in there. This is the electronic configuration. Now to draw the molecular orbitals, the s orbitals are going to overlap with each other, and when they overlap with each other, see, when they overlap with each other, they're going to form the bonding state. There are two possibilities here for the atomic orbitals. The atomic s orbitals can either overlap with each other. If they overlap with each other, you're going to form the bonding state. They're going to form the bonding state if they overlap with each other. This is the sigma bonding state. Now, if they don't overlap with each other, then in that case, you're going to form the anti-bonding state. Remember that for every bonding, there is an anti-bonding molecular orbital. So here, what I formed in the center is basically my molecular orbital in there. On the sides, the 1s's are my atomic orbitals. In the middle, the sigma and the sigma star, these are my molecular orbitals. So if I ask you, draw the molecular orbital diagram of hydrogen, then the molecular orbital diagram of hydrogen is going to have two molecular orbitals. It's going to have one for the sigma and the other one for the sigma star. For every bonding molecular orbital, you do have an anti-bonding molecular orbital. Now, normally the anti-bonding molecular orbital is higher in energy, and this is why its basically its state is going to be higher because the energy increases as you go up. Now, with respect to the filling the electrons in the molecular orbital, it's basically the sum of the electrons that are present in the atomic orbital. So in the atomic orbital, I have in each s orbital, I have one electron. So you start filling your bonding molecular orbital first, and the maximum capacity for the molecular orbitals is 2 electrons. And when you represent the electrons, we are representing the electrons here as a spins. And when we combine the spins together, we want them in opposite directions so that do not repel each other. So you go ahead and you fill your bonding state. The bonding state is going to have the lowest in energy, so you're going to fill it first. Now we are out of electrons because we filled all our electrons in the bonding state, and the anti-bonding state will have no electrons in there. So to draw the molecular orbital, that's it. This is going to be it, showing the bonding and the anti-bonding molecular orbitals, and the bonding state has 2 electrons in there. In this chapter, we are interested in the molecular orbitals for double bonds and conjugated systems, since we are working with conjugated systems in there. So the rule says that in order to figure out how many pi molecular orbitals you have, you're going to check how many p atomic orbitals you have, because the numbers are the same. So the number of pi molecular orbitals is equal to the number of p atomic orbitals. So let's say I gave you ethene. Ethene is the simplest alkene. Ethene is not conjugated. It is not conjugated. It has only one double bond in there. So to figure out how many pi molecular orbitals you have for ethene, you want to see how many p atomic orbitals you have for it. And I know that the double bond is the overlap of basically of 2p orbitals. So when my p orbitals overlap with each other, so these are my p orbitals in there, when they overlap with each other, every p orbital has 1 electron. When they do overlap with each other, I'm going to form my pi bond. So ethene has a max of 2p orbitals, so I'm going to end up having 2 pi molecular orbitals for ethene. Now I want to go ahead and draw them. And to draw the pi molecular orbitals, you would need to draw the p atomic orbitals first. Now each of the p atomic orbitals for the carbon has 1 electron. Why? It has 1 electron. So I'm just explaining in here why we have 1 electron in the p atomic orbital. You have to draw the electronic configuration of carbon, do hybridization and excitation, and then figure out how many groups are connected to the carbon in there. You have 3 groups, so you would need 3 atomic orbitals. So since you need 3 atomic orbitals, then you need to hybridize these 3 atomic orbitals. You're going to be left with 1 electron in the p orbital there. So every p orbital, for every carbon, you do have 2 carbons in here for ethene. So you would need to write a carbon in there and a carbon in here. And we are only considering the p atomic orbitals for each of the carbons. So each p atomic orbital has only 1 electron. These electrons can either overlap with each other, and they can make now not the sigma, because p orbitals, when they overlap, they make the pi bonding state. So they can either make the pi or the pi star anti-bonding state. And now you start filling your electrons. Make sure that the lower energy pi bonding state has a max capacity of 2 electrons in there, so you will be left with nothing for the anti-bonding molecular orbital. So now if I want to draw the molecular orbital of ethene, you don't have to show the atomic orbitals, the p atomic orbitals, just show the middle ones, the pi and the pi star. So we're going to show them over here. Normally with the pi molecular orbitals and the pi, which is basically the bonding and the anti-bonding molecular orbitals for pi, we give them a name. So the name is basically corresponding to the bonding state. So bonding states are occupied states, and anti-bonding states are unoccupied states. So we're going to start naming the highest molecular orbital that is completely filled or that is filled. We're going to name it as the highest occupied molecular orbital, HOMO. This is highest occupied molecular orbital. It's the highest molecular orbital in the example that you are working with that is occupied. And then above it, always above the highest occupied molecular orbital, there is the lowest unoccupied molecular orbital in there. Why do I care about these two? I care about these two because in every single conjugated reaction, in order to check if the reaction happens or not, you need to draw the molecular orbital of your conjugated system, and you need to look at your highest occupied molecular orbital and the lowest unoccupied molecular orbital. If there is a bonding states between them, if they bond with each other, then basically you will form a reaction between them, and you will form a reaction between them, and you will form bonds. If they don't interact with each other, or if they are not in a bonding state with respect to each other, then there will be no reaction. So we will talk about this, and I will give you a couple of examples on those. But first, let's explain the concept of how we draw the molecular orbitals in there. Now, drawing the molecular orbitals, you need to show the p orbitals overlapping with each other. Now, this diagram in here, we call it the frontier molecular orbital. The frontier molecular orbital is when you show the p orbitals overlapping with each other. So the p atomic orbitals overlapping with each other. This is called the frontier molecular orbital there. Now, with the bonding state, normally the p lobes are in a bonding mode. So the lobes, the upper lobes, need to have the same sign or the same shade, and the lower lobes, they also need to have the same sign or the same shade in there. So normally what I do, we shade them the same shade, so that to show that they are in the bonding state. So this is going to be the bonding state. B stands for bonding. And then for the anti-bonding state, you show the lobes basically not overlapping with each other. If they don't overlap with each other, then this means that they should have opposite signs in their lobes. And A stands for the anti-bonding state in there. So as I said, whenever you're doing any reaction, you would need to consider the highest occupied molecular orbital for the nucleophile and the lowest unoccupied molecular orbital for the electrophile. So search, where is your nucleophile? Draw its molecular orbitals and pick out the highest occupied molecular orbital there. Where's your electrophile? And then draw its molecular orbital and pick up the lowest unoccupied molecular orbital, and then see if there is any bonding between the highest occupied molecular orbital and the lowest unoccupied molecular orbital for both. If there is a bonding state, then this means that the reaction can happen between them and bonds can form. If there is no bonding, then this means that the reaction cannot happen. So let's draw now, let's kick it a notch and draw the molecular orbital for a conjugated system now for 1,3-butadiene. So again, as the rule, this rule will help you a lot because it will help you figure out how many pi molecular orbitals you are going to draw. So we said that every double bond is an overlap of 2p orbitals in here, right? This is what we said. So you have 2p orbitals, you have a p orbital here, you have a p orbital here for every double bond, another p orbital, another p orbital, and every p orbital has one electron. So I have here a total of 4 p orbitals. So this means that I will have 4 pi molecular orbitals. So start drawing your 4 pi molecular orbitals. So as you can see over here, I didn't draw the p atomic orbitals and did the overlap, showing the bonding and the anti-bonding states. You don't have to do this. All what you need to do is just draw the molecular orbitals in there. I knew that I have 4 pi molecular orbitals, so start drawing the 4 pi molecular orbitals in a form of pi 1, pi 2. So you just divide them by 2 over here, and each two are going to be, the first two are going to be in the bonding state. For every bonding at a molecular orbital, there is an anti-bonding molecular orbital. So pi 1 has a pi 3 star anti-bonding, and pi 2 has a pi 4 star anti-bonding in there. You draw always the bonding molecular orbitals as a lower energy, and then you have the anti-bonding molecular orbitals as a higher energy in there. So whatever I'm showing here, pi 1, pi 2, pi 3, and pi 4, this is the molecular orbital diagram in here. Now, molecular orbital diagram is not complete unless you fill it with electrons. So we know that each p atomic orbital has one electron. So we have a total of basically here 4 electrons. So we have 4, we say we have 4 pi electrons in there. So we would need to fill those 4 pi electrons. Every molecular orbital has a capacity of 2 electrons. So we would fill 2 electrons in the pi 1, we would fill 2 electrons in the pi 2, and then we are done with respect to the electrons. So now we want to figure out for the butadiene, where is our highest occupied molecular orbital? The highest occupied molecular orbital definition is it's the highest molecular orbital that is completely filled, okay? So or it is filled, it doesn't have to be completely, but it's the highest occupied molecular orbital that has electrons in it. Now the highest occupied molecular orbital that has electrons in it is pi 2. This is the highest molecular orbital that has electrons. So this is going to be pi 2, so I'm going to label it highest occupied molecular orbital in there. Now normally underneath it, the pi 1 will be called lowest occupied molecular orbital. So as I said, the occupied, the O, the occupied in here, we use it to represent the bonding state. The unoccupied, we use it to represent the anti-bonding state. Above the highest occupied molecular orbital, you have the lowest unoccupied molecular orbital in there. And these two are very important, the highest and the lowest unoccupied molecular orbital. So with that, I would be done with my molecular orbitals. Now for the frontier molecular orbitals, I have to draw them in a form of lobes, showing the p orbitals overlapping with each other. So we're going to start with the lowest occupied molecular orbitals. We know that we have 4 p atomic orbitals, right? So we have to draw the 4 p atomic orbitals. We have 1, 2, 3, and 4 over there for all. Now in the lowest occupied molecular orbital, all the p atomic orbitals, they do overlap with each other. So you have a bonding state in there. Everything overlaps with each other. Going to the highest occupied molecular orbital, and this is how I want you to draw them, each two are going to overlap with each other. So the first two are going to overlap with each other. The second two are going to overlap with each other, but the ones in the center, they don't. So basically what you have here, you have one node. You have one node, which is basically the anti-bonding. A stands for the anti-bonding, where there is a possibility of not finding an electron. So the node is the possibility of not finding an electron, and there is a possibility of not finding an electron where the possibility of not finding an electron basically is here. It's between these two, p orbitals. There's a possibility of not finding an electron over there. So we're starting with 0 node for the lowest occupied molecular orbital, and this is always as it's going to happen. You're going to start with a 0 node, and as you increase in energy, the number of nodes is going to increase from 0, 1, 2, etc. Now with respect to the lowest unoccupied molecular orbital, when we want to draw them, only the centers are going to bond, and then the p orbitals on the edges, these are not gonna be in the bonding state. So make sure that you bond the centers. So in this case, I want to make sure that the top lobes of the center p orbitals, they have the same shade. And then this is going to make the p orbitals on the edges. These are going to be different shades than the one in the center, so that I can have my 2 nodes in there. And the highest unoccupied molecular orbital, there is no bonding between any of these p orbitals. So basically you have 3 anti-bonding states in there. This is one interaction, It's going to be 1, 2, and 3, so you're going to end up having 3 nodes. So normally reactions, why do we care about conjugated systems and the molecular orbitals? Because as I mentioned at the beginning, that we would need to consider the molecular orbitals in order to explain if reactions happen or not. So reactions happen between the highest occupied molecular orbital of the nucleophile and the lowest unoccupied molecular orbital of the electrophile. So you have to locate where your nucleophile is, where your electrophile is, and do the interaction between them and see if you have any bonding states. If you have bonding states in there between the highest occupied and the lowest unoccupied, this means that the reaction can happen. If you have anti-bonding states, this means that the reaction will not happen. Or anti-bonding interaction, this means that the reaction will not happen. So let me give you an example. Now, Diels-Alder reaction is our next section in there that we will explain, but I'm going to explain the molecular orbitals for the Diels-Alder reaction before that. So consider the Diels-Alder reaction. This is a reaction between a diene and a dienophile. A dienophile is a system that has only one double bond. And it's telling me, consider the Diels-Alder reaction between 1,3-butadiene and ethene. Does it happen? So the 1,3-butadiene is here, the ethene is there. And it's asking me, does it happen? Now, first I would need to pick up which one is my nucleophile, which one is my electrophile. Now, the one that has more double bonds, I know that a double bond is a nucleophile, but the one that has more double bonds is going to be my nucleophile. And the one that has less double bonds is going to be my electrophile in this case. Okay? So I know that this is my nucleophile, so I have to draw its molecular orbitals and pick the highest occupied molecular orbital of the nucleophile. And do the same thing for the electrophile and pick the lowest unoccupied molecular orbital of the electrophile. And then see if there is any sort of bonding interactions or anti-bonding interactions between them. So you start by drawing the molecular orbital diagram for the 1,3-butadiene. So as we said, in the first state, pi 1, all the p orbitals, they do overlap with each other. In the second state, the highest occupied molecular orbital, each two, they overlap with each other. And in the third state, only the centers, they overlap with each other. And then in the fourth, none overlap with each other. So basically, you're going to end up having 3 nodes in there. So you're going to end up having 3 anti-bonding interactions between them. I don't care about any of them. All I care about is the highest occupied orbital that is filled in the nucleophile state. So the highest occupied molecular orbital that is filled after I fill my electrons. I know here I have 4 pi electrons, so fill your 4 pi electrons, 2 in pi 1 and 2 in pi 2. So now pi 2 is my highest molecular orbital that is occupied. So this is going to be the HOMO for the nucleophile. I would need to consider that. And then for the electrophile now, I do have 2 molecular orbitals because I have 2 p orbitals for the double bond. So you draw them, and I do have pi 1 and pi, you can either name this as pi 1 star, or pi 1 pi 2 star, whatever you want. And then I would need to consider the electrons. So I am having 2 electrons in the pi 1. So my pi 1 is going to be my highest occupied. So immediately above that, you should have your lowest unoccupied molecular orbital. Now, for the electrophile, I would need to pick my lowest unoccupied molecular orbital. With the lowest unoccupied molecular orbital, you don't have an interaction between the p lobes in there, so you have an anti-bonding state. So you go from a 0 node to 1 node in here, okay? So now the question is, does 1,3-butadiene react with ethene? So as I said, we're going to take the highest occupied molecular orbital. So all I did is I took the highest occupied molecular orbital of the 1,3-butadiene. I just drew it exactly as I have it up there. So just go ahead and draw it, okay? And then take the lowest unoccupied molecular orbital of the ethene, and that is it. And now see if the reaction is going to happen. If you're going to form a bond, if you're going to form a sigma bond, you're going to form a bond between carbon 1 and this carbon, and between carbon 4, okay, and between carbon 4 and this carbon over here. So in order to check if there is a bond that could be formed, you need to check if the p orbitals can overlap with each other. If they overlap with each other, this means that they have the same shade, then you have the bonding state in there, so the sigma bonds can be formed. If not, then the sigma bond cannot be formed. It's enough to have one anti-bonding condition, one anti-bonding overlap in order for the reaction to be forbidden. So, so in here, let's see, the shades are the same. So I have basically this part of the lobe is shaded, this part of the lobe is shaded. So when the ethene slides underneath the 1,3-butadiene, these two lobes over here, they're going to overlap with each other. And when they overlap with each other, they're going to form the bonding state. So we do have a bonding interaction here between these two lobes. Now between these two, again, imagine the ethene sliding underneath the 1,3-butadiene. So basically this lobe and this lobe are going to be under each other. So they're going to bond each other. So I have here two bonding interactions. So both interactions are bonding. So yes, reaction will happen. And this is an example of Diels-Alder reaction that we're going to study in the next section. And with Diels-Alder reaction, it happens in presence of heat, where the bond between carbon 1 and 2 forms a double bond between carbon 2 and the 3, and the double bond between the 3 and 4 opens up to form a bond between 4 and 5. So see, this here, this is 4, and this is 5. So I have a bonding state between 4 and 5, and since my lobes, they overlap with each other, so yes, the bond between 4 and 5 happens in this case. And then between 6 and 1, this is basically the 6 and the 1 over there. And look at the 6 and the 1. The 6 and the 1, they do overlap with each other. So yes, a bond can happen between 6 and 1. So the product always for Diels-Alder reaction is a cyclohexene. This is the product in there, where a bond can form between 6 and 1, and we proved it using molecular models, and a bond can form between 4 and 5, and we proved it using molecular models in there. Let's have another example. And in this other example in here, it's telling me that I do have a cycloaddition, okay, reaction of two ethane molecules, and I want to form a cyclobutane. Does it occur? Can this happen? Whenever you're going from double bonds to a cycle, always consider the molecular orbital. We're going to use the frontier molecular orbitals. Before drawing the frontier molecular orbitals, I'm just going to go ahead and draw the molecular orbitals for ethene. So what you have here is my ethene. This is my ethene over here. I know that I have 2p atomic orbitals, implies I'm going to end up having 2 pi molecular orbitals. So I'm going to draw 2 ethenes in here, because since I'm reacting 2 ethenes with each other, okay, so I'm going to have my 2 pi molecular orbitals for each one of them. I know that the first pi molecular orbital is going to be pi 1, and the second pi molecular orbital is going to be pi 2 star for each one of them. This is pi 2 star. Okay, the molecular orbitals are going to be the same, but I would need one to be a nucleophile and the other one to be the electrophile for the reaction to happen. So let's see if the reaction happens or not. So for the pi 1, I know that alkene, the ethene in here has 2 electrons, right? 2 electrons. It has 2 p orbitals. So this is a carbon-carbon. And I do have here 2 p orbitals. So this is going to be my p orbitals over there with 2 electrons for the alkene. So pi 1 has a capacity of 2 electrons, and I have 0 electrons in the pi 2 star. That's it. Same thing for the ethane here. It has 2 electrons in the bonding state and 0 electrons in the anti-bonding state. So this is going to be my bonding state, and that is going to be for the anti-bonding state for both. Okay, so let's go ahead and draw the frontier molecular orbitals. So the frontier molecular orbitals, I have 2 p orbitals over there, right? And those p orbitals can either completely bond with each other. This is going to be the bonding state. or they cannot bond with each other. So I need to show opposite shades for both lobes in there. So that is going to be the anti-bonding. The top one is going to be the anti-bonding state, and the bottom one is going to be the bonding state in there. So if I want to consider that first ethene, this first ethene in here, I want to pick up the highest occupied molecular orbital. So the highest occupied molecular orbital for the first ethene, it's going to be this one. This is going to be the highest occupied molecular orbital because it does have 2 electrons in there. And this is the molecular orbital that is occupied. So the first ethene acts as a nucleophile. I have to pick its highest occupied molecular orbital. So let's go ahead and draw the highest occupied molecular orbital. So we're going to draw it like this. Now we're seeing if there's a reaction between the 2 ethenes in order to make the cyclobutane. So this is my 2 ethenes over here, and this is my highest occupied molecular orbital of 1 ethene. Now I want to look for the lowest unoccupied molecular orbital for the second ethene, and the lowest unoccupied molecular orbital is going to be pi 2 star for the second ethene. So that is going to be my lowest. This is going to be my lowest unoccupied molecular orbital. So here this is going to be the same. Nothing is going to differ because both are the same. They are alkenes, this ethenes. So that is going to be my lowest unoccupied molecular orbital. The unoccupied molecular orbital is always above the the highest occupied molecular orbital. So this is the highest occupied molecular orbital there. So I'm just going to go ahead and pick the lowest unoccupied molecular orbital for my ethene. This is going to serve as my electrophile. My highest occupied molecular orbital is going to serve as my nucleophile. Why I am targeting the lowest unoccupied molecular orbital? Because this is an electrophile. An electrophile are not supposed to have electrons in there. They're going to accept electrons from the nucleophile. So the nucleophile should be filled with electrons and the electrophile should not. Or they should have less electrons than the nucleophile so that they can accept more electrons from the nucleophile. So the lowest unoccupied molecular orbital for the second ethene now has the frontier molecular orbital that looks like this. Here you go. So let's go ahead and draw it. So this is it over here, and this is the bottom lobe is shaded. Now, as you can see, I did put them underneath each other. This is the lowest unoccupied molecular orbital, and now I want to check if there's a bonding state in there between the lobes. So between those two over here, yes, there is a bonding state. So in between those two lobes, no, there is no bonding state in there. There is no bonding state. There is an anti-bonding state. So you write it like this, and you write it as an anti-bonding state. The moment that you can see the p orbitals, they don't bond with each other, this means that the reaction is forbidden. So here we should say your reason, reaction is forbidden because there is an anti-bonding state. There is one anti-bonding state between 2p orbitals. Okay, so as long as you have one anti-bonding, so if everything is bonding, all the p orbitals are bonding except 2p orbitals are not bonding, you have one anti-bonding state, then immediately the reaction will not happen. Reaction happens when the p orbitals, they overlap with each other. All the p orbitals, they do overlap with each other for both the nucleophile and the electrophile, because see, with this type of reaction, see what you're forming. You are reacting, these are my dienes over here. So basically you are making a new bond between this carbon and this carbon. Let's label them. This is 1, 2, 3, and 4. So what you're doing here, you're using the double bond between 1 and 2 to make a new bond between carbon 2 and 3. And you're using the double bond between 3 and 4 and making a new bond between carbons 1 and 4. So if 1 and 4 can bond, so here what I have is carbon 1, carbon 4. Carbon 1 and 4, they can bond with each other. But carbons 2 and 3, they can't. So this means that the reaction we say is forbidden. It cannot happen. So over here, this is why you have X. This means that the reaction cannot happen. We say the reaction is forbidden. So this is just an overview of molecular orbitals. Once we go into benzene, we're gonna hit on molecular orbitals again. This is the max that I want you to know with respect to molecular orbitals. You're gonna go further in details with molecular orbitals if you decide to take inorganic class.